Hey guys, welcome to the fifth episode of High School Math Fundamentals by Charles here. So, what I'm gonna do first before I get into solving trigonometric equations is just gonna review the radian system here. Okay, so we have our Cartesian plane here, right? And we have some arm, right? And an angle theta, right? So it's known that when we're talking about radians here, this is going to be 0 radians. This is pi over 2 radians. This is pi radians. And this is 3 pi over 2 radians. And this is also, this can be 0 or 2 pi radians. Okay, 2 pi radians is 1 full rotation here. Okay, and so that would mean that in between here, this is pi over 4. Over here, we have a 3 pi over 4 when the arm is there, so that's halfway in between there. And then over here we have 5 pi over 4. And over here we have 7 pi over 4. Okay. So most of your special angles are in here. There is pi over 6, which is a special angle too, which means you'll be able to find the sine, cosine, tangent of that angle pretty easily. So pi over 3 is a special angle 2, pi over 4 is a special angle, pi over 2, etc. Okay, and all the variations of the over 4s here, over 2s are also special angles. Okay, and I'm also going to review our cast rule here. So cast rule tells us in what quadrant every trigonometric function is positive. So we start in this quadrant down here, quadrant 4, and we put a C, right? Because cosine is positive here. Cos is positive. A up here, because all are positive. S up here, because sine is positive. And T down here, because the tangent is positive, right? And when tangent positive, sine, cosine are negative. And here, sine and tangent are negative. And here, cosine and tangent are negative. Okay? So let's get started solving some trigonometric equations here. Okay, so I'm going to start off simple. Label this A, I guess. We have the tangent of x, which is what we're solving for. It's 1 over root 3. Okay, and to isolate for x here, you would just take the inverse tangent of both sides. 1 over root 3 there. Okay, and we know that tangent pi over 6, which is a special angle, is actually equal to 1 over root 3. And if you ever forget what the tangent of pi over 6 is, you can draw this triangle here. Okay, and so we have sides of 2 here. It's an equilateral triangle, should mention that, which means this angle here is going to be pi over 3 radians. It's going to be pi over 3 radians as well, and it's 60 degrees. An equilateral triangle has all angles 60 degrees. This is going to be half of 60 and half of 60, so that's 30 degrees, or pi over 6, radians, and that's pi over 6 radians. Okay, and so we want the tangent of this pi over 6 here. Okay, so we know that the tangent of pi over 6 is going to equal our opposite over adjacent, right? The opposite is half of 2, so that's 1. And our adjacent is this guy here. But how do we find that? So this mystery adjacent we'll call A. So A equals 2 squared minus 1 squared by Pythagorean theorem. That's A squared. 4 minus 1. It's A squared. So that means A is equal to root 3. And therefore tangent of pi over 6 is root 3. Okay. So that's you can do the same thing for pi over 3 here to find your trigonometric ratios. You can also use this right triangle here with an angle of 45 degrees, or pi over 4 radians here. Pi over 4 radians, or 45 degrees, to solve it as well. With hypotenuse, side length 1 and hypotenuse root 2. Okay, so erasing all of this now that we know how to do that, let's solve this first equation here. So this expression is asking the tangent of what angle is 1 over root 3, and we just found out that it's pi over 6, right? So x is pi over 6. But actually, we're not done yet. I'll set restrictions on x actually first. I'll say x belongs to the closed interval 0 to pi. Okay? So keeping that in mind now, we have two solutions, because now we're considering all possible angles within one rotation for the angle. So x could be pi over 6, but where else is tangent positive, right? This is a positive 1 over 3, right? So we know we know pi over 6 is in this first quadrant here, where all of them are positive by cast rule. But where else is tangent positive? In the third quadrant down here, right? So we need to find an equivalent kind of angle for this third quadrant here. To do that, here we have pi over 6, right? It's going to be like a straight line. Like imagine a straight line through, and that's that angle there is going to be also pi over 6, right? But we got to add this remaining part, and that remaining part is just pi, right? Because we set up here, pi is kind of like a half of a rotation. Okay, so let me just get rid of that. Okay. So, keeping that in mind now, we also know that the answer to this could be pi over 6 plus pi. But we don't want to keep it like that. So, pi over 6 plus 6 pi over 6, because that's just pi. So, x is equal to pi over 6, or 7 pi over 6. Right, and you don't actually have to put all the steps there. It's something you can just do in your head. But I just showed it there so you can see how I did it there. Okay. Let's do another one now, I suppose. Let's do 3 times the cosine of x is equal to the cosine of x minus 1. Okay, so I would start by moving or collecting the like terms here. want to move this right cosine of x over to the left side. So let's do that. 3 cosine of x, subtracting a cosine of x on both sides, equals just -1 on that side now. Okay, and now we're going to have 2 cosine of x equals -1. So dividing both sides by 2, we get the cosine of x is equal to -1 over 2. Okay, so isolating for x now, we get x is equal to the inverse cosine of -1 over 2. Okay, and now we need to ask ourselves what special angle. All these examples are special angles, by the way. If they're not, then you will probably be permitted to use a calculator, unless you are solving using compound angle formulas, but not in this case. So the cosine of what angle is -1 over 2? Well, we know that to be pi over 3 by that triangle method that I showed you guys earlier. Okay, but it's negative. Slight problem, right? It's negative 1 over 2. And now we need to ask ourselves where, when x belongs to the interval 0 to pi, which, by the way, is the same thing as saying 0 is less than or equal to x is less than or equal to pi. Okay, so where within that interval is the cosine going to be negative, right? Cosine's positive here, we don't want that. Cosine's positive here, we don't want that. So it's just these two quadrants. Okay, so pi over 3, right? Pi over 3. We want equivalent angles here. Okay, so pi over 3, it's about here. And then same thing for down here. Okay, that's pi over 3. And here is pi over 3 as well. Okay. So we again have two possibilities, right? This first angle here we want to find, this green one, and we also need to find this one, because in both cases the cosine of it is going to be negative, right? But pi over 3 is like the core angle in both cases. So to find this green one here, we're going to do pi minus pi over 3, right? Because we have pi over 3 here and we have pi here. So pi over 3, pi minus pi over 3 is this, what we're looking for. Okay, and that's just 2 pi over 3. And then for this blue one, we're going to have pi, that's pi, and that's pi over 3. And we're finding the whole thing. So we know we're going to be adding pi plus pi over 3, which is 4 pi over 3. Right, so now we know x is equal to 2 pi over 3 and 4 pi over 3 within that interval. If you didn't have a restriction here, you could have infinite kind of possibilities for this, because if you look at the cosine function here, it just keeps oscillating forever and ever, like indefinitely, right? And it can be the answer to it, like when it's -1 over 2, right, that's around here. There's infinitely many times that this function, cosine of x, is equal to -1 over 2. But we're setting restrictions on our domain here. So we only have 2 answers. Okay, so let's do another one then. We will do, I suppose, sine squared of x equals sine x. Okay. Let's move this to the other side here. So we'll subtract sine x on both sides. So we just get it all on one side. Looks to be better. And so we can maybe try and factor something out. And we can. So we can factor out a sine x. And then left we have sine x minus 1. Okay. And yeah, note that sine x is sine squared x. Or you could also write it like sine x all squared. But most people use this here. Okay. So now we have kind of two solutions here, two possibilities, because this could be 0 or this could be 0, right? So we have sine x equals 0 and sine x minus 1 equals 0. Okay, so when is sine, so let's isolate for x here, inverse sine of 0, and so sine x equals 1 because we're adding 1 to both sides, and so x is the inverse sine of 1, right? And our domain again is x belongs to the interval, closed interval, 0 to pi. Okay, and so now we're asking the question here, when is the sine of when is the sine of x equals to 0? I'm not sure if I was saying that before, but yeah, when is the sine of x equal to that, right? That's what this inverse is kind of asking, right? So in this case, let's look at it here. Our Cartesian plane again here. When this arm is at 0, when it's 0 degrees, our sine, the sine of the angle is also going to be 0 at 0 here, because that's the way the sine function looks here, right? We also have a 0 at pi over 2 here. I'm sorry, pi, my bad. Not pi over 2. At pi over 2, sine is 1. Okay, so let's write all those down. Oh, and since we're including 2 pi in our interval, we can actually include 2 pi here. So we will write 0, pi, 2 pi as our answers for that one. We still have more to go. So when the sine of what angle is 1 here? So actually we just said it's pi over 2, right? So our solutions, x equals 0, pi over 2, pi, and 2 pi, right? Because we have no other solutions for this. Within that interval, sine of x isn't 1 anywhere else. So and another thing you will probably be required to do is proving trigonometric identities, right? But actually, before I get to that, I'm gonna do one more here. Just one more. Okay. So we will do root 2 sine x plus tangent of x equals 0. Okay. So I don't like these two distinct things here. This is going to make it very difficult. So I'd rather switch this tangent x into sine x over cos x. And the reason I'm doing that is so I can factor out a sine x. Right? And in my brackets now I have root 2 plus 1 over cos x, and that's equal to 0. Right? So now we have two solutions again. That can be 0 or that can be 0, right? So sine x equals 0, and we already said the inverse sine of 0 within the interval, keep forgetting to write this down, sorry. X belongs to 0 and 2 pi. Within that interval, x here, the inverse sine of 0 will yield 0 pi or 2 pi for x. Okay, and or we have root 2, just this equals to 0. Root 2 plus 1 over cosine of x equals 0. Right? So let's subtract root 2 from both sides. Negative root 2 here. Okay. And let's just cross multiply. So negative root 2 cosine of x is 1. So negative 1 over root 2 is cosine of x, and because we're dividing both sides by negative root 2, and so x is the inverse cosine, just taking the inverse cosine of both sides, of negative 1 over root 2. Okay, and our solutions for this, that's a special angle here. It corresponds to a special angle, 1 over root 2. It is pi over 4. Okay? But it's negative, right? So we need to look at our Cartesian plane here, at our cast system. C-A-S-T. Right? So it's positive here, we don't want it. It's positive here, we don't want it. Negative here, negative here. Right? So we know it's going to be a third quadrant angle and a fourth quadrant angle with these restrictions here. Okay? So, what did I say it was? Pi over 4. Right? So that'll be here and here. Pi over 4 and pi over 4. Okay? That one is 5 pi over 4 here. Suppose I write it down there, 5 pi over 4. And then up here is 3 pi over 4. And I'm getting that by the method before, use up here. Okay? Because it's this angle and this whole angle. Those are the two distinct angles. So we have our answer then. 3 pi over 4 and 5 pi over 4 for those. Okay. All right, now let's prove one trigonometric identity. Okay. Whenever you're proving identities, you're going to want to have a left side and a right side. And basically, you're going to try to manipulate either the left or right side to be the same thing. And if you can't, then they're not equal, and you've disproven the identity. So we're going to do tangent of x plus y multiplied by the tangent of x minus y. And that is sine squared of x minus sine squared of y over cos squared of x minus sine squared of y. Okay? And we're trying to see if this is actually equal to this. We're trying to prove this, essentially. We're given an equation, and we want to, see why it's right. Okay? So I'm going to do left side. You can choose to either manipulate the left side or the right side here. It doesn't really matter. You can do it either way, I think, in this case. Tangent x minus y. But I think more often than not, one will be easier than the other. sine squared x minus sine squared y over cos squared x minus sine squared y. Okay. So, how are we going to manipulate this now? Let's just, for questions like these, you kind of just have to try a lot of things, and you have to kind of think outside the box. But I think what most people would try first, and it's actually what is correct to do, is use the compound angle formulas for tangent here. Okay, and so the compound angle formula for tangent of x plus y here then is tangent x plus tangent y over 1 minus tangent x tangent y. And when you have a difference, it's kind of like you're just switching the signs there. So that's being multiplied by tangent x minus tangent y over 1 plus tangent x tangent y. You'll most likely be given the formulas for these, but yeah, on like an assessment or something. But yeah, that's how you do that. And so let's just put this all in one fraction here. 10y, that's all being multiplied by 10x minus 10y over 1 minus 10x tan y, 1 plus 10x tan y. Now right now it kind of looks like we're going nowhere. We've only gotten more messy, but I promise it'll it'll get better. Okay, so we're gonna simplify, or we're gonna expand rather, the numerator and denominator here. Okay, because we'll get some things that cancel out. So do FOIL, binomial expansion here. We are going to get tan squared of x plus tan y tan x minus tan y tan x, and then we are going to have minus tan y, or squared, tan y squared. And these two are actually going to cancel. That's all over 1 minus tan x tan y plus tan x tan y. And then we will have minus tan squared x tan squared y. Okay, and these are going to cancel out, so let me just rewrite this now. Tan squared x minus tan squared y over 1 minus tan squared x tan squared y. Okay, so we have sine and cosine here. You know, might be a good idea to start including that now, right? Because if we don't switch the tangent to sine and cosine, how are we going to get to this, right? So let's do that now. I feel like now is a good time. We will do sine squared of x over cos squared of x, because that's tan squared of x. And then we'll subtract. I would do the same thing to this one. Oh, this is actually y. No. Over cos squared of y. All over 1 minus, and we'll do it with both of these here, sine squared of x over cos squared of x times sine squared of y over cos squared. of y. Okay, great. So we are going to get a common denominator here, and kind of combine that into one fraction. And I guess we could do something similar. I mean, in the denominator as well. But let's do the numerator first here. Okay, so sine squared of x times cos squared of x. Sorry, cos squared of y over cos squared of x times cos squared of y, which is multiplying both sides, both the numerator and the denominator here, by cos squared of y, because that's how we get a common denominator with that one. And that's going to be subtract sine squared of y multiplied by cos squared of x over, we are going to have the same thing, x cos squared of y. Okay, so that's just our numerator, actually. That's still all over. And I guess it would probably be a good idea here to kind of expand this as well. So this one I'm going to turn into a cos squared x cos squared y over cos squared x cos squared y, right? Because that's just one. It's same thing divided by itself, it's just one. And then that's subtract sine squared, and I did that by cos squared x cos squared y, because when I multiply these, I'm going to get the same thing. Common denominator, right? So sine squared x, sine squared y, because I'm multiplying them, over cos squared x, and then cos squared y, right? And they're a common denominator, so I'll just actually combine them now into one bigger fraction on both sides. And it happens to be so that we have a common denominator in the numerator and the denominator of our bigger fraction, if that makes sense there. So what we can actually do is cancel these out, because you're dividing by the same thing in the numerator and the denominator. It's like multiplying by the same thing in the numerator and the denominator. Sine squared y cos squared x all over cos squared x cos squared y minus sine squared x sine squared y. Okay? And so now if you notice, we'll be able to kind of factor a couple things out here. Or I suppose actually after before we do that, I will use the Pythagorean identity to get rid of some of these cosines here. I suppose yeah, that's a good way to say it. Okay, so sine squared x cos squared of y, that's just 1 minus sine squared y minus sine squared y multiplied by 1 minus sine squared x. Okay, that's just the Pythagorean identity, because sine squared x plus cos squared x is equal to 1 using the unit circle. Okay, and so it's all over cos squared x multiplied by 1 minus sine squared y. That's by the same Pythagorean identity. And we'll do it here too, I suppose. We'll change this into a cos. Cos squared x times sine squared y. Okay, that gets us closer to where we want to be here. Okay. And I believe this is actually supposed to... Oh no, that's good. That's good. Okay. So, next now, we can redistribute a couple of things here. So, sine squared x minus sine squared x sine squared y. I'm just distributing it. Minus sine squared y minus, or it's actually plus sine squared x sine squared y. Yeah, that's correct. Okay. So that's all over. Cos squared x minus sine squared y cos squared x minus sine squared y plus sine squared y cos squared x. Okay, now we can cancel a couple of things out here. This cancels with this. Okay, they're the same term, and they're equal and opposite there. And at the bottom, in the denominator here, we have this sine squared y and cos squared x, and this one too, and they cancel out. And so, rewriting it now, it's sine squared x minus sine squared y over cos squared x minus sine squared y. And is that what we have up here? Sine squared x minus sine squared y over cos squared x minus sine squared y. Yeah, that is what we have. So with the trigonometric identities here, you're always going to want to just try a couple of things out. If it doesn't work, then you might have to try something else. But just try and steer yourself in the right direction, pretty much. Okay. Right. That's it for this lesson. It's a lengthy one, but I hope you guys found it helpful. Thank you.